All right. So that's kind of the more in-depth technical side of Coulomb's law. But Coulomb's law also has a lighter side to it. So what I'd like to do now is to think about that lighter side. But this isn't all just for fun. It actually starts to point at some deep philosophical issues and get us into some interesting kinds of paradoxes, actually, whose philosophical resolution ultimately comes from that principle of superposition. So this isn't all just for fun and games, but it's still kind of a really fun and neat demonstration. And you're going to have a chance to look at similar phenomena actually when you do the first lab. And also you can find these kinds of videos out there on YouTube. So I encourage you to try to take a look out there. Just make sure you're looking at good stuff when you go look at YouTube. So here's an example of a phenomena I want us to think about. And here, let me just play the video for you a little bit. And so what you can see here is sort of a standard electrostatic demonstration of a metal can, an aluminum can, right? And if you listen to the video, if you find it on YouTube, what you'll hear is all the people oohing and eyeing, because it's really just kind of a fun, neat demonstration. And hopefully as you're watching it, it's kind of putting a smile on your face too. It's just neat. But what is it that makes this thing neat? There's something really mysterious about it, actually, isn't there? I mean, what makes it neat, what puts a smile on our face, is just the fact that we're able, it's like magic, right? We're able to move the can without actually touching it. Now, how does that really work? There are really sort of philosophical and physical reasons why we know that's actually not possible. It's not possible to influence something without having some kind of direct contact with it. Or is it possible? It looks like something else is happening in the video. Well, this gets us into this interesting philosophical issue known as action at a distance. And it's actually fairly problematic as a concept. Actually, even the early philosophers of the scientific revolution, right, the late scholastic philosophers, really had a problem with this concept of action at a distance. They had good, sound philosophical reasons for thinking, really, that it was just impossible. In fact, there were two people who really hated this idea of an action at a distance. It was outright rejected by two very famous philosophers, both of whom you've heard of, and both of whom actually we couldn't do this course without. The first is Descartes, who of course is responsible for the Cartesian coordinate system that we were just using in this example that we had just gone through in some depth. And also Leibniz, the inventor of calculus, and that notation we use all the time, dy over dx, that notation that sometimes drives your math professors kind of crazy. They believed this action at a distance was completely impossible. But they found some sort of clever ways around it. And I don't want you to think that it's just them. In fact, now that we understand relativity, if you think about the consequences of relativity and action at a distance, if there really truly could be action at a distance where one object can just reach across empty space and have a force directly on another object, then you can get into all kinds of interesting paradoxes where the causes of effects happen after the effect, where causality is backwards, right? And we just know the universe doesn't work that way. If you're traveling like on a long car trip with your little brothers and sisters, say in the back of the car on the family vacation, and one of the little ones goes and punches the other little one and says, and the parent says, why did you hit your sister? And the guy says, well, because tomorrow she's going to pull my hair. Well, that's not really an excuse, right? The cause cannot happen after the effect. But with relativity, if you combine relativity with this action at a distance, you can actually get into situations where the cause would happen after the effect. So this whole thing becomes very paradoxical. We'll actually look a little bit at special relativity later on in this course. But for now, I just want to point out that this idea that one thing can act on another, very far away, that does have some real philosophical problems. And Descartes actually had a very interesting way of getting around this problem. They weren't thinking about action at a distance in terms of electromagnetic theory, but they were thinking about it in terms of gravity, because Newton had just worked out the orbits of the planets. And it was very mysterious in his universal theory of gravitation how the sun can just reach out and have an influence across empty space on the planets. So I want to show you what Descartes came up with to try to get around this action at a distance. It's something called Cartesian vortices. And I want to point it out to you because actually his conception isn't too far off from the modern physics conception of how we address this problem. So I really do have a lot of respect for these sort of late medieval philosophers. So here's how Descartes got around this idea of Cartesian vortices. So say here's the sun, S, here in the middle, and over here is some planet. Maybe this is the planet Earth. And the question is, well, how can the sun reach out across this empty space and influence the orbit and put a force on the Earth? And Descartes' answer was these vortices. So what he said was, no, that's not actually what's happening. That might look like what's happening, but what's actually happening is that the sun somehow is stirring up the space around it, creating some kind of like whirlpool or vortex around the sun. And there's no action at a distance there because the sun is actually in contact with that area of space. So then it stirs up this vortex. That was his view. And then this vortex can stir up another vortex through direct contact with that vortex. Again, no action at a distance. And this secondary vortex might set up a tertiary vortex here. And finally, a quaternary vortex that, how did this guy come here? That's really nice. A quaternary vortex, just ignore that. A quaternary vortex that then is in the direct location of the Earth. And that it's that contact with that vortex that the Earth actually feels, and which is what actually drives the Earth around the sun. So you can see there's this idea of getting around action at a distance by always having just local contacts here between the sun and its local area, between local areas in themselves, and finally between a local area and the Earth, completely eliminating the need for action at a distance by the introduction of this kind of special property of space, a vortex that might exist at any particular point. Very good. So now I want to try to make this a little bit more formal and bring this up to our modern world by taking a look at how we look at this now in modern physics. And it actually is going to take us directly back to what we had seen earlier in terms of the principle of superposition. So let me write that down a little bit more formally mathematically. Principle of superposition again, but mathematically. So I'm going to have a superposition, a general situation where I might want to apply the principle of superposition. So here's sort of my most generic situation. I'm going to have some charge, capital Q, right? And I want to compute the force on that charge, kind of like in our previous example. But now I'm going to have a whole arbitrary collection of various different charges, Q1, Q2, Q3, blah, 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 Q, all the way up to Q capital N. And now, of course, I have to specify precisely where all these charges are. So once again, there's going to be an origin. There'll be a vector that tells me the location of Q. I'll call that vector R. There's going to be a vector that tells me the location of Q1. I'll call that R vector 1. Another one that gives me Q2, R vector 2. etc., all the way through R vector N. Now, mathematically, what the principle of superposition is saying is that when I want to compute the force, capital F, on that charge Q, I do it by simply adding up the interactions from each of the individual charges as though they were only pairwise interactions without any interference. So all that means is then I simply sum over all the charges in my system, lowercase n goes from 1 up to capital N. And what I sum up then is my standard Coulomb formula for the force coming from each of those charges. And for now, just because the notation is much more compact and precise, I will write this down in the Cartesian form, but you can write it down whichever form you like. The form you remember, though, says that I'm going to have Coulomb's constant, K sub C, right, times the product of my two charges. In this case, it's capital Q times little q sub n, because I'm dealing with the nth charge at the time while I'm adding all these up. Then I have the displacement vector from q sub n, which sits at Rn, to my location R. So there's a minus sign, right? Normally we can think in our mnemonic this might be a little arrow pointing that way, right? But it's R because that's the charge I want, and I want the vector that goes from Q1 towards Q to get the proper direction. And then finally, remember, I have to divide by the distance. And notice here, this is the distance cubed. Some people get a little confused when they first see this Cartesian form because I have a third power in the denominator. Because we remember Coulomb's law goes like 1 over distance squared, you think, wait, why is this cubed up here? Well, remember, though, this is the Cartesian form, so I also have a vector in the numerator that has a length to it, right? This is a displacement vector. So there are units of meters up here. And then you have to divide by meters cubed so that in the end, you are actually dividing by the distance squared. So it's consistent with your standard trig form for Coulomb's law. So this, then, is how we would write out the total force on any given charge using the principle of superposition. Now, here's the interesting thing, and here's how we can get out of this action at a distance problem. I want you to think for a moment about how this force depends upon the charge Q. Here's a quick example to get you thinking, right? Suppose you're part of some engineering firm, right? And the boss gives you a whole collection of charges like this and says, okay, Jones, I want to know the force on charge Q. You've got a big calculation to do. I need the results on my desk by tomorrow morning. Fine, whatever. So you go ahead, you calculate everything, you come up with some force, he gives you some charge, capital Q is 1 Coulomb, and then now the force is 3 newtons. Fine. Then he comes back a few days later and says, oh, I'm really sorry, the design team screwed up. Thanks for that 3 Newton answer, but the problem is the charge capital Q that we need is not 1 Coulomb, it's 2 coulombs. I need you to redo this whole calculation from scratch. And if you're sitting there thinking about it for a moment, you're thinking, wait, no, this is silly, right? I mean, come on. All he did was he just doubled the charge Q, right? I don't have to redo this whole crazy calculation. Everything's proportional to Q, right? If I double the charge Q, I'm just going to double the total force of my result. It's not going to be 3 newtons. It's going to be 6 newtons. Wow. That's a very key observation. Notice the way this is structured. I could simply factor out that charge, capital Q. So let me do that mathematically. I can pull the charge out of the sum. This is the distributive property, actually, of addition. So I can rewrite this as Q times this handy proportionality constant. And this proportionality constant, once I calculate it, it's easy to calculate the force on charge Q. I can just multiply whatever charge capital Q I'm given by this extra proportionality constant that I'm writing down here. That's the first thing to notice. It's a very simple formula for getting the total force proportional to the charge. The second thing to notice is what this proportionality constant depends on. It depends upon, of course, the arrangement of all of these charges in Coulomb's constant. It depends on the charges Qn, their locations Rn, the Coulomb constant Kc, right? But there's only one other thing it depends on, which is vector R, which is the location of charge Q. So let's write this down then. It's a proportionality constant. Notice it's a vector result because I've got vectors in the numerator, and I'm going to call it vector E, and that vector E depends only on location R. And this is a very key mathematical form. And there's a special name given to this proportionality constant. This is what is known as the electric field. And what I want you to notice is that this electric field is set up by all these other charges. Fine. It depends upon them. But it depends, beyond the arrangement of charges, it depends only on the location of the charge Q. And this corresponds then precisely to Descartes' view of these Cartesian vortices, right? The idea here now, I can get rid of action at a distance. I don't have the force on Q, right, depending upon some reaching out across empty space of influences from all of these different charges, as I would have it when I write down the sum this way. But when I rearrange it into this form with an electric field, the force on charge Q depends only on Q and the value of this field at the location of Q. There's no more action at a distance in this particular final formula. What I do have to begin to accept, though, is the idea that there's this special property of space, this electric field, which can physically push and pull on charges and generate forces on them. But it can do that locally because it exists at the location of the charges. So that's the basic concept then of the electric field, and we will explore that more in our next lecture.